But these J0 to JLs, these are subsets of alphas, subsets of the indices for these monomials. And then the D0 to Dm minus 1, those are just positive integers. And we define a new Dm, the next term in the sequence, to just be 0. And from this upper Rado functional, we construct a polynomial, g, of w. This is a single variable polynomial, where we take the sum from 0 to m, this m here, the degree of the functional, of q to the di is coming from the functional, and dm being 0, of these portions of the original polynomial, right? Instead of summing over all alpha, we sum over the alpha that are contained in a specific j. C alpha, that's the coefficient we had before, but then instead of n variables, we just let all of the variables be the same. So w is x1, x2, xn, and then this term just turns into w to the size of alpha. So after constructing this polynomial, it should have a real root inside of the interval 1 to q. And again, this has to happen for every q bigger than or equal to 2. As we saw last time, the choice of upper Rado functional does matter. It is possible to pick one functional for which the polynomial does not have a root in this interval, and then pick some other functional for which the resulting polynomial does have a root in this interval. And we also mentioned last time, in response to Andreas's question, this condition can be checked for any polynomial. Now, the amount of work you will have to do to check it could be quite large. It could be a lot of work to determine every possible upper Rado functional and then examine every possible polynomial and show that it does or does not have a root inside of 1 to q. But it is doable in a finite amount of time.
Well, how is it, because you're quantifying over q, right, which is an infinite set, so how do you only check finitely many q?
Actually, that's a good point. So I guess it's not actually checkable unless you're in a lucky enough situation that you can use a general technique to handle all q at once. At the very maybe if you suspect that your polynomial results in an equation that's not partition regular, then you only need to find a single q for which this does not happen. And then that could be checkable if you have some information as to what q to guess.
I'm wondering why this maximal Rado condition is interesting, because, you know, the theorem gives you the fact that it's satisfies the maximal Rado condition, but that seems less interesting for our purposes than partition regular. So it seems like the way this theorem is being used is actually in its contrapositive. You show something's not that it doesn't satisfy the maximal Rado condition, and then it'll tell you that it's not partition regular.
Yes, that's correct.
And in that case, yeah, you only have to check a single q. But then you have to quantify over all the upper Rado functionals. I don't know.
Well, so I agree with everything you said, and maybe the remark to put all of this together is that the upper Rado functionals are independent of q. So the first thing you would do if you wanted to show that some equation is not partition regular is you would have to find every upper Rado functional. And the technique I showed last time should generalize. Namely, let me not get into it right now. I can go back to that at the end if we have some time. But if you use the inhomogeneous linear Rado theorem along with the homogeneous Rado theorem, then you should be able to work out every possible upper Rado functional. It may be a lot of work, take a lot of time, but I believe it's doable. And then once you have the upper Rado functionals, you can try to pick some ideal Q that will result in a polynomial that does not have a root in one.
Okay. Okay.
Any other questions or remarks about the condition before I delve into the proof? Okay. So first I'm gonna go through the proof in broad detail, and I'll underline places where there's more details to check. And then at the end, I'll come back and I'll check those details and get into the weeds. But I would like to do the overview first. If I skip something and don't underline it, but you still want to hear about it, you could tell me, and then I'll underline that as well, and we can discuss it at the end, or possibly at that moment. Now, the first thing, one of the, I guess the last result that I mentioned at part 1 of this talk, which is what's going to allow us to go from ordinary Ramsey theory into Ramsey theory on the non-standard integers, is that the polynomial equation, p of x1 to xn equals 0, is partition regular over the integers if and only if there exists some non-standard numbers, xc1 to xcn, which are infinite, indiscernible, and such that they satisfy this equation. Now, I put the infinite in red because I copied this from both the paper I'm using from Barrett, Lupini, and Moreira, as well as I checked it with this other paper I believe I sent you guys after the first talk. Although I do think you need the extra assumption that this polynomial doesn't have trivial solutions. I mean, I guess I'm already getting into the weeds here, but I feel obligated to mention this. Right, this polynomial is partition regular because for any partition of the integers, one of the cells will contain the integer 2, and that's going to be a solution. And therefore, the non-standard numbers that would give you solutions, it's just going to be 2. That's it. And that's going to be finite, not infinite. But if you avoid something as trivial as this, then these guys are going to end up being infinite. And we do use the fact that they are infinite. That is part of the reason that we're going to non-standard numbers, as we're going to see in a moment. But point being, we can just assume this is a non-trivial equation. It has infinitely many solutions. Now,
can you remind what indiscernible is too?
Certainly.
Thank you.
So these two numbers are indiscernible if for any set of natural numbers, we either have that C1, C2 are in the non-standard extension, the hyperextension of this set, or both of them are not in the non-standard extension of the set A. So what this means is you cannot distinguish XC1 and XC2 only using information from the natural numbers.
And
If you want to,
the hyperextension means that like A is a set in C1 and C2.
and the analyst definition of the hyperextension
Okay. Yeah, right. Gotcha. Thank you.
There was that equivalence relation. You have to mod out using some ideal generated by ultrafilter, but we only consider those sequences where all elements are coming from your set A, and that's going to be the hyperextension of A. And again, since we're on the topic, it never hurts to refresh that if the natural numbers are partitioned, well, I guess I shouldn't start at 1, then that partition induces a partition of the non-standard natural numbers. I mean, I don't think I use this fact. This fact is maybe wrapped up into this statement here, but still an interesting fact to refresh on. Okay. Any other questions before I continue? So I guess I should make one more comment. This fact is already one of the steps where the magic of non-standard analysis is coming into this proof. I told you guys in part 1, we proved one direction, which I consider to be easy, at least easy if you're comfortable with the definitions, but I still don't know how to prove the other direction, namely the direction that we're using right now. We know, or we're assuming that this polynomial is partition regular, and I still don't know how to prove that these indiscernibles exist, but the fact that we can get our hands on some concrete numbers that are not changing instead of some unknown solution to this equation that depends on the partition, this concreteness is the beginning of the benefits of this non-standard proof. It's very similar to ultrafilters as well, but you know what, I'll save that comment for later. I do want to, at the very least, go through this proof, and then we can have more discussions afterwards. Okay, so now we assume the polynomial is partition regular. So we take our indiscernibles, they're indiscernible and they are infinite. And now we fix our q bigger than or equal to 2 from the statement of the maximal Rado condition. And now we take an infinite number nu such that the first new digits in the base q expansion of these indiscernibles agree and are equal to sigma. Now, I will go into this in more detail, but just to give you a vague idea as to what's happening here, you could partition the natural numbers by assigning each number to its first non-zero digit in base q. And there's only q minus 1 non-zero digits in base q. So this will split up the natural numbers into q minus 1 sets. If you extend this coloring appropriately to the non-standard numbers, then you can again get a partition based on the non-zero digits mod q. But now the magic, the power, is that instead of the first non-zero digit or the first n digits starting at the non-zero digit, we can get an infinite number of digits. And so I should maybe clarify here. And maybe this will be more clear when I write it out on the next slide. What this means, we can write each of our non-standard numbers in this form, right? You take out the largest power of q, which divides your number, and then this sigma is the first new locations, and those are going to give you excuse me, dang it, no. This is actually for the minimal Rado condition. This was correct as written. Yes, sorry. This makes perfect sense as written. First new digits. But right. So just to give you a concrete example, if you took this number, which is 46, you could write it in base 5, and then if you factor out the largest power of 5 that occurs in the base 5 expansion, then we get all of this stuff here. And this is like the sigma, right? We're taking out the largest power that appears in the expansion, right? So this corresponds to this, and then sigma corresponds to this. And now this part hasn't shown up yet, but this is just all the leftovers. Now, the other thing we notice after we stipulate that these sigmas are the same, because the xc's are indiscernible, is that these exponents are also indiscernible. So again, I guess I was using this color. So the exponents are infinite, since the original xc's are infinite, and the exponents are also indiscernible. And just the general idea for what's happening here is so the reason that these exponents are indiscernible is, given a partition of the natural numbers, you can make a new partition where you look at an integer, you take its base q expansion, and then you look at the largest power that occurs in the base q expansion, and you determine whether that power is or you determine which of the AIs contains that power. And then that's going to give you a set BI. So my point is, instead of whenever you partition the natural numbers, you could also make a partition based on these exponents mod q. But all of these partitions will not distinguish the x's. And therefore, if this does not distinguish the x's, if I go back to the original coloring, it will not distinguish the exponents, the taus.
I have a question about this indiscernible condition again.
Yes.
So the way I'm thinking about it is that, you know, a non-standard number is, you know, just a sequence, of course. So is it saying that all of the, like, a number occurs in one sequence if and only if it occurs in the other sequence? Is that what indiscernible means? Like, you have a 1 in xc1 if and only if you have a 1 in xc2 for all ones.
Kind of, but I don't know. I think you have the right idea, but you're being a little vague. So a 1 appears. That part.
Yeah, it's an element of the sequence.
What sequence? You mean if I was to write it out? Write out.
Yeah, of xc1, it's a sequence. Yeah, so one of the x's is a 1 if and only if an x of the other xc is a 1.
No, because these sequences are equivalence classes. They only have to agree on a set that's contained within some ultrafilter that was formed in the beginning.
Okay.
So
you have to have a large set of ones. A p large.
I don't know a more concrete definition of indiscernible.
Yeah, because the definition you gave is just kind of like, I'm surprised that anything does that off at first blush. But
maybe I guess it would be helpful to show you an example of two indiscernible.
Yeah.
But I actually don't know of an example of two indiscernible numbers. Because how would you check that for any partition there, or for any set A, they're either both contained in star A or not contained in star A?
So it feels to me, this might be wrong, but the idea I had is maybe you want basically the digits of the two numbers to agree along some different ultrafilter. So you have your fixed ultrafilter that you're using to define your non-standard numbers. And then to get some sort of partition property, it seems like maybe you want like a second ultrafilter along which digits agree. But I don't know that that's going to be consistent as you start adjusting. Like when you take equivalence classes, I don't know if that actually works.
Yeah, that shouldn't be helpful, because if two ultrafilters are different, you can take a set contained in one of them, but not the other. So for all we know,
yeah,
these two things agree on a set that's contained in the ultrafilter we use to define it, but not in the other random ultrafilter that you picked.
Yeah, so I guess that doesn't work either. Then I don't know.
So
that's it.
I guess the way that we're using this indiscernible property is that any property that can be distinguished via a partition is not going to be distinguished between these numbers. So I think I wrote, well, I think I just said this out loud, but if you were to It might just be helpful for me to write it again. So So you could partition the natural numbers based on the first digit in the, or the digit of the largest position in the base Q expansion, the largest non-zero position. And this partitions the natural numbers into n, into Q minus 1 sets. So since these x's are indiscernible, there is some I that contains all of them. And you know what? Why stop at 2? Okay. Which would mean that the well, so first of all, I am glossing over one detail. I haven't explained base Q expansions for non-standard numbers. But let me continue glossing over that. Hopefully we all like base Q and we can just accept that. But since I could make a partition like this, it extends. I guess I should put the star here. And then the star is just going to consist of all of the non-standard numbers where the first digit appearing in their largest base Q expansion is equal to I. Now, okay, this last claim here, I suppose that this does need to be checked. It may not be totally obvious. It's obvious if you use like transfer from set theory, but it can also be checked directly using the sequences definition. But this particular part I would like to delay until later. But hopefully, what I'm hoping to communicate to you right now is the way in which the definition of indiscernible is being used. And hopefully I have communicated that, but if not, I would be happy to answer questions on that, because I think that is one of the key things to learn about this whole benefit of non-standard numbers in Ramsey theory.
Sohail, what is the definition of being a member of A star? Is it p-lim of one, the indicator function of A, C, and K equal to 1? Is that what it means? Meaning that the times where you belong to AI is P large.
Yes, yes. The times that you belong to AI is P large.
So then indiscernible means that the P limit is 1 or 0 for all of them, meaning that it's 1 for all of them or 0 for all of them. Is that what it is?
Well, first off, you might not be able to you can't take a p limit because these are infinite numbers.
No, that's why I'm using 1a, 1 over a indicator function of a, and inside of the stomach of that function, you put the members of the sequence.
Yes.
So it's bounded.
Yes. Okay. So then you are correct. The p limit will either be 1 for all of them or it will be 0 for all of them. Yes.
Okay. All right. I guess that helps make it simpler for me.
Yeah. Any other questions, comments, concerns? And I guess since we already stopped, I might as well mention. I maybe should have mentioned this beforehand, but this partition, this idea of partitioning based on the initial non-zero digits is on one hand not novel, on the other hand it shouldn't be surprising. So the reason it shouldn't be surprising is if you have read the proof of the original Rado theorem for linear equations, then the partition that he uses to show that things are not partition regular when they do not satisfy his condition is based on not the beginning digits, but it is based on the ending digits, the smallest non-zero digits of your number. So that is what the original Rado theorem was based off of. And that was useful because you could take things mod p or mod p to the k for a large enough power of k, and then you would just lose all of this stuff here, and then the partition worked out. So the fact that we're working not with the smallest digits, but with the largest digits seems fairly reasonable. It's not it didn't come out of nowhere, but it's still surprising because we cannot take things mod p to the k to get rid of this stuff here. So that's, in my opinion, the reason why we don't see this coloring or this partition used in ordinary Ramsey theory is even if these things agree, you still have interference from the smaller digits, and we don't know how to get rid of that interference when it's coming from the smaller digits. We only know how to get rid of it from the larger digits. But as we continue, the magic of non-standard analysis is what's going to allow us to get rid of this small interference. And the minimal Rado condition does use the coloring scheme that was used in the original Rado theorem, but the proof is slightly more cumbersome and technical due to technical reasons that I will not get into. So point being, this is the ideas here are genuinely connected to the ideas that Rado used in his original theorem. Okay. So that being said, we have written each of these xc's in their base q expansion. We factored out the largest power of q from each of them. And we know that the first new digits agree, where nu was infinite. So all of those are going to be sigma, right? All of these things are going to be the same. And then all of the remainder, it's just going to be something that is in between 0 and 1.
So wait, because maybe I didn't get something. When you said sigma, you with this orange color, you underlined the full expression on the top. So I thought that this sigma just corresponds to the constant term. Constant meaning the first one, the 1.
So maybe I should here. I should probably just continue this example.
By the way, how do you call the letter when you write writing? How do you call the letter writing in the first sentence?
Xi.
Xi, without e. Xi.
Sorry.
Kusu. Xi.
Okay. Thank you, Andres. I should have, this is probably a more instructive example now. Right. So if we wanted to just put things in the same partition class based on the first two digits being the same, then we see that both 46 and 146 start off with digits of 1 and 4 in their base 5 expansion. So if I put it into this form, you take out the largest power of 5, so 5 squared and 5 cubed. The sigma would just be the 9/5 in both cases. And then this is going to be here, right? So these parts. And yeah. Well, should maybe right, so 1/5 squared is going to be the q to the negative nu, and then the 1 or the 1/5 is going to be the rho j. So these taus are indiscernible. That was the comment we made here. So now we can define this functional. This is what showed up in the definition of upper Rado functional. And this is now a functional from the non-standard numbers to the non-standard numbers. And the fact that these are infinite and indiscernible corresponds to the fact that we wanted for every finite coloring of n and every r, there exists infinitely many C monochromatic positive linear maps that do this. So that infinite and indiscernible takes care of that condition from upper Rado functional. There's probably no hope of me going through the details of why that works, but for now, take my word on it, and we'll see what we can do about it later. So we have the functional, and now we take an increasing enumeration of the image of this functional over the alphas that appear in the support of our polynomial. Thankfully, the non-standard numbers are still linearly ordered, just like the ordinary numbers. So we can make an increasing enumeration. And now we consider the first t for which m0 minus mt is infinite. Right? M0 minus mt could be any non-standard natural number. We have no clue. And we know that m0 minus m0 is 0, so that's finite. So for some t between 1 and L, this thing might be infinite. Or if it's never infinite, that's also fine, right? If m0 minus mt is finite for all of these t's, that's not going to give us any problems. Now, so we pick that m, whatever it is, and we define zeta j to just be what's left from C after we remove the power. And the sigma is going to be something between 1 and q, which is hopefully obvious from here, from the concrete example, right? Because this digit is at most 4, this digit is at most 4, this digit is at most 4 if I was to continue. So the largest value you could get is just 4 plus 4 over 5 plus 4 over 5 squared and so on, which would sum up to just be 5. Even if you were to start adding, right? So if you were to add q minus 1 over q to the v for every possible non-standard number, the sum of the standard numbers over the standard numbers would give you q, and then all of the non-standard parts are infinitesimal, so they're not gonna make it any bigger than q. But we're not even taking this infinite sum, so well, I guess it could actually be equal, not that it makes a difference. And then w, the root of our polynomial from the maximal Rado condition, is going to be the standard part of this sigma. Okay. So hopefully everything will start to come together here. I know I might have made you suffer a lot up to this point, but hopefully it'll be worth it now. So we've set everything up, and now, well, okay, I guess one more piece of setup. We partition our polynomial based on the partitions given to us in the upper Rado functional, right? These JTs partitioned the support of the polynomial. So now for each t, I'm going to let qt be the portion of the polynomial we started with whose support is contained in jt. So then essentially by definition, well, first by assumption, 0 is the polynomial evaluated at all of our x's. That was at the very beginning of this proof. Now, by definition of these q's and the j's, this polynomial is going to be the sum of these q's evaluated at all of the x's. And sorry, this should be q depends on n inputs, not 1. And now the benefit of this is that I can pull out q to the mt from all of these, little q. So remember the right? This is not just any partition. This is the partitions where the functional applied to alpha agree. They're all equal to the same number. The functional was actually what we get from plugging all of these x's into the polynomial. So maybe I should write this out. Huh. The little scissors thing is not there. Well, okay. So if I plug in each of these exceeds into the monomial, and then each of these exceeds the largest power of q that occurs in the base q expansion is q to the tau 1, tau 2, tau n, then here I'm going to get that the largest power of q that appears here in the evaluation is tau 1 alpha 1 plus tau 2 alpha 2 all the way up to tau n alpha n. So I'm going to pull that entire power of q out. They all add up to mt by assumption. And all that's going to be left is this zeta portion that's between 0 and 1. So basically, we specifically partitioned the support in such a way that that when I factor out the largest power of q from each term, and it's the same, I'm going to group all of those terms together. Now I split this up. You can see first I split it up by the m. So the first m terms I keep on one side, the other m plus 1 to l terms I move to the other side. And after I split it in half, I divide everything by q to the negative m. So this is where the second magic or the second power of non-standard analysis comes in. The fact that I'm capable of dividing by an infinite number. So this division is well defined, and the definition of this m, this little m, was that each of these is infinite, right? mt minus mm is negative and infinite for all of these values of t, by definition. So this is equal to q to the negative infinity, and this is actually somewhat rigorous. It's just q to a negative infinite non-standard number. However, each of these zetas was between 0, actually, 1, 1. Each of these zetas are bounded. So if I evaluate the polynomial at some bounded numbers, I get a bounded quantity. And if I divide that bounded quantity by an infinite natural number, it becomes infinitesimal. So the magic is we've gotten rid of all of these terms using infinitesimals. We see that they're infinitesimal. So this original polynomial here, for all of these t's where t is between 0 and m, this difference was finite. Right, so anytime the difference is finite and equal to an integer, we keep it. Anytime the difference is infinite and not equal to an integer, it just turns out to give us something infinitesimal and we can throw it away. So now this polynomial, when we evaluate it at zeta 1 to zeta n, is going to be infinitesimal. And then here I'm using the fact, this is one of the other facts that I said was pretty crucial in the very first part of this talk, where so we saw earlier that each of these zeta j's is equal to some sigma plus an infinitesimal number. So that's why I can replace each of these with the sigma, and then the difference between the original and the new expression is just going to be some other infinitesimal. This is essentially the statement that polynomials are continuous, therefore you could exchange the infinitesimals on the input for some infinitesimal on the output. So this is another location where the power of non-standard analysis is being used, because I stated here, I stated that this partition based on the initial digits has not been used in Ramsey theory so far, or at least I have not seen it, because we don't know of a way to get rid of these error terms. But using non-standard analysis, those error terms turn out to just be infinitesimals, and then that's how we get rid of them. So that's another piece of magic, or something that I really don't know how to replicate in ordinary Ramsey theory, and why I think that this proof really needs non-standard methods. This fact here and this fact here, both of those are really make crucial use of non-standard analysis. And that's basically the end of the proof. I mean, I guess I have one more line where so if 0 is approximately equal to this, if they differ by infinitesimal and they're both bounded, which they clearly are bounded numbers, then their standard parts agree. So I take standard parts of each side. Standard part of 0 is just 0. So it'll also be the standard part of this expression. This, I believe we also mentioned on the first talk, just again, this is kind of like the continuity of polynomials is being used here. The fact that polynomials are continuous is what lets you move the standard part from outside to inside. And then we already defined the standard part to be the W. So if you just unravel your definitions, then you can get this expression here, which is what we had in the statement of the maximal Rado condition. And that's the end of the proof. So that did take a little bit longer than I thought, because I didn't check any of the details that I said I would check with you. But first, are there any questions about this proof? Hopefully, I'm hoping at the bare minimum, I conveyed the importance of these two steps. The fact that we can rigorously divide by an infinite number to get rid of some terms of our polynomial and ignore them. And the fact that some of our error terms, some terms that we wanted to ignore, we could ignore because we were able to rigorously identify them with infinitesimals, which can be neglected. So those are two crucial ideas that appeared in this non-standard proof that I don't know how to replicate in ordinary Ramsey theory. So I'm hoping I could at least convey that much to you, regardless of all those other details that I did not check. But that being said, are there any questions about anything that I've said so far? Okay, then I will end the recording at this.